So, if you've ever tried to build a microbial fuel cell, you probably know that feeling, the frustration when you get really weak results. Well, today, we're going to skip all the super complex theory and focus on what really matters, the design. We're going to put together a practical blueprint that actually works, one that turns waste into watts, every single time. Let's jump right in. Does this look familiar? Come on, you know what I'm talking about. You've set everything up perfectly, you've waited and waited, but that multimeter just isn't showing the numbers you were hoping for. It's a super common headache that makes you second-guess everything. But what if I told you the problem isn't the chemistry? What if it's all about the design?
Yup, you heard that right. A lot of the time, that weak performance has nothing to do with your microbes or the complex reactions. It's all about the physical way you put the cell together. See, top-tier performance comes from a top-tier blueprint, and in this explainer, that's exactly what we're going to build, step by step.
All right, our first stop is the big one. This is probably the most fundamental choice you're going to make, and it pretty much dictates everything else. The cost, how complicated it is, and of course, how much power you get. Welcome to the Great Chamber Debate. Just look at this breakdown. The trade-offs are incredibly clear, right? The dual-chamber design, yeah, it gives you a ton of control, but it comes at a huge cost. It needs this special barrier, a proton exchange membrane, which creates a ton of internal resistance. And you know what that does? It just kills your power output. The single-chamber design, though, it's an absolute powerhouse. You expose the cathode right to the air, get rid of that expensive membrane, cut your costs, and you can get power densities up to 5 watts per cubic meter. It's a no-brainer. And hey, you don't have to take my word for it. The research on this is really clear. As the expert Bruce Logan pointed out way back in 2009, if you care about performance, power, and building something practical yourself, the single-chamber design is, without a doubt, the winner. It just makes the whole process easier for the electrons and protons, which directly juices your power. Okay, so we've picked our architecture. Single-chamber it is. Now comes the really cool part, the fine-tuning. These next couple of things, the spacing and the volume, are the real secret to unlocking your design's full potential. And wow, this chart says it all. Just look at that difference. All we did was shrink the distance between the anode and cathode from 5 centimeters down to 2, and we literally doubled the voltage output. That is a tiny physical change with a massive electrical payoff. So, why does that happen? Well, it's all about minimizing something called ohmic drop. Just think of it like electrical friction. It's the resistance the power has to fight to get from point A to point B. The shorter that journey, the less friction there is, and the more power actually makes it. So keeping your electrodes between 1 and 5 centimeters apart, that's the sweet spot. You slash that internal resistance without getting in the way of that all-important biofilm on the anode. Now, the second piece of our power puzzle is volume. You can get okay results with a bunch of different sizes, but the data consistently shows that the peak power density, that's the most watts you can squeeze out of your volume, is almost always found in chambers between 200 and 300 milliliters. It's kind of the Goldilocks zone for balancing the fuel and the microbes. So, we have our architecture and our dimensions are locked in. Now we got to talk about what we're actually building this thing with. Getting the materials right is absolutely the foundation of your MFC. You need good conductivity and something that's going to last. Okay, for your anode, you want something that microbes can easily latch onto and that conducts electricity well. So carbon-based stuff like carbon cloth or graphite felt is perfect. For the cathode, its main job is to speed up the reaction with oxygen, so it needs a little help from a catalyst. For the chamber itself, just go with something durable and non-reactive. Acrylic is a great choice. And hey, if you really want to push the limits, you can look into advanced materials like graphene to seriously boost that performance. We've gone through the chamber design, the dimensions, the materials, so now let's put it all together. Let's create one final actionable blueprint that you can walk away with and start using right now. Here it is, your recipe for success. First, just commit to that single-chamber air cathode design. It's simple and powerful. Second, nail that spacing. Get it in the sweet spot between 1 and 5 centimeters. Third, pick good carbon-based materials for your electrodes. You got to give that power-producing biofilm a happy home. And finally, and this is important, remember you're working with living things. Design your system to keep conditions stable, ideally around 25 to 35 degrees Celsius and a nice neutral pH. That's it. That's the whole game plan. So there you have it, a complete design blueprint for building a microbial fuel cell that actually, works. The science behind it is amazing, for sure, but a great design is what really brings it all to life. So the only question left is, now that you have this blueprint, what are you going to power first?